All right, anyways, the quizzes are graded and in, but there's still a few people out there that have not made it up yet that have to. So I'll give it back to you guys later in the week once I have all of them in. But overall, there was a lot of perfects and pretty close to perfects. When I pass them back, we'll go over some common little mistakes that were here and there, but overall it was pretty good. So we're going to move along, go over questions on the two-part problems, ask whatever you have, and then we're going to move on to the last part of the chapter today that's called free fall. We still have another lab in this chapter and probably a day of concept builders, so the big tests won't be till sometime next week. I'll give you a day closer to the end of this week when we do some other stuff. All right, so anyways, open your books to whatever page is on 71. And just remember back from like Thursday or whatever it was when we went over this stuff. Two-part problems, well, they obviously have two parts, right? One part is always going to be constant velocity, and one part is going to be accelerated motion, speeding up or slowing down. All right? Just remember, we did one example together, and those could come in any order. And I warned you about that. Don't think every problem is going to be a carbon copy of the one we did. And some of them were closer than others, but they all at least had the fact that there was a constant velocity and an accelerated motion part. And another thing I warned you is just read carefully. Constant acceleration is not the same thing as constant velocity, right? That's for some people that stopped by for some help in the last, either on Friday or earlier today, I think that's where some of them were getting tripped up on. Right? If it says constant acceleration, that just means you are accelerating. You're either speeding up or slowing down, whatever it says. And some of the times it doesn't say the words constant velocity. It implies it through what you're reading, so you got to read everything carefully. So you had 30 through 33 and 36, right? The only one that was pretty different was 33, and that's because you almost had to work it backwards a little bit. But still consider the type of problem we did in the example. So let me read the answers. We'll go over whatever ones we have questions on. Number 30, you should get somewhere close to 252.5 or something very close to that. 4,252.5 meters. Number 31, you should get around 27 meters. Number 32, you should get somewhere around 1,160 meters. 33.077, or if you rounded to .008, that would be fine too, meters per second square. And finally, 36, close to 34 meters. All right, so questions. Yes, 33. All right, so this is on, and the hint is you almost have to work it backwards a little bit. It says we're training for an upcoming 5-kilometer race. That number is going to be important soon. We start out training to run by moving at a constant pace of 4.3 meters per second for 19 minutes. So right there, that's constant velocity, right? We're maintaining a velocity of 4.3 meters per second. Has to be a velocity since it's meters per second, right? For 19 minutes and staying steady at that. That's the definition of constant velocity. And then we accelerate at a constant rate until we cross the finish line 19.4 seconds later. What is our acceleration? So this is the only one that didn't ask for distance. But we still got to think that way, just work it backwards. So first of all, let's just make sense of the situation, regardless of the numbers. It's a longer distance race, right? What do you do in a long distance race? Even if you didn't do it before, it should make sense. I've never been involved in one before. It would be impossible to run your fastest the whole time, or try to speed up the whole time for a long race, right? So what do? You run at your best pace for the longest stretch, right? And then somewhere when you are approaching the end, then you turn it on and try to rush to the end, right? Or accelerate. That's what's going on here, all right? But the whole race is how far? 5 kilometers. But that 5 kilometers, again, is the entire thing. It's going to be broken up. So in all of our other problems, we found two different D's and added them together, right? To find a total D. Well, this is the total D. We got to figure out from the information how we break it up to eventually get where we need to go. All right? So I'm not going to list 5 kilometers as a given in either column straight up just yet. So let's start. We do have constant V first. Because the V we ran at was 4.3 meters per second for a time of 19 minutes. And we should probably immediately, as long as we catch it, change that to what, guys? Seconds. When we convert 19 minutes into seconds, what does it come out to be? Go ahead. 1,140? Everybody else get that? Make sure we're same page. Alright, and then is when we get to the accelerated motion portion of it. And remember, a lot of times, I won't say 100% of the time, but most times there's some kind of crossover piece of information. If I'm running at that most of the race, then I speed up at the very end. That constant velocity becomes my what in this column? Yes. Initial velocity, right? Because that's what I'm speeding up from. But we want to be very careful. Am I allowed to put this T over here? No, this time was just the time I was running steady at that. Do not put that T over here. It does not apply. All right. The time is given over here. The last little bit of the race, which makes sense because you can't speed up forever, like the last 19.4 seconds go over there. And I'm going to do something like I was doing with D's and other problems, just so you don't get things confused. Since there's two T's and they represent two different numbers in each part, I'm just going to subscript this one with a 1 and a 2 just so we don't get them confused. They're two different ones, right? And I need to find that acceleration rate. But looking at what I have, I can't straight up find that. If I tried to go to this column right now and tried to find A, I'm in trouble because to use any one kinematic equation, you need at least how many givens? Well, they have 4 in them, but to solve for 1, you have to have at least 3, right? We only have 2 values over here in the accelerated motion column. So that doesn't mean it's unsolvable. That means we got to figure out something to do. All right? What could we figure out? Well, there's one. We have 2 of the 3 things over here because this is constant. You have to use what equation for constant velocity all the time? What's the one equation that's the only one we ever have? Yeah. Right. V equals d over t, and we obviously have v and t. They're not telling me to solve for d, but I warned you guys in many problems, you have to find things they don't ask you for in order to find what they are asking you for. So sometimes you still don't know what to do, but start looking, what could I find, and how could it be helpful? So that's something I could find, right? I can't find anything right now using this stuff, because I would need at least 3 things over there given. So that's the only thing I could find. Let's see how it helps me and what it means. So I'm going to solve that equation for D, and I'm going to just say D for part 1 as well, because there might be a D for part 3. D1 is equal to V times T1, right? We rearrange that form, simple little formula, V equals D over T, and plug in 4.3 times 1140, the time after we convert to seconds. And somebody that did this and got this far, tell me what they got. Yeah. Good. 4,902 meters. Now, how in the heck does that help me? We need it, but why? That still doesn't, that's the D for the constant velocity part. That doesn't directly help me here yet. Carly? Exactly. Here's where the 5 kilometers comes in. All right. Remember, the 5 kilometers total wasn't this part or this part separately. It was both of them together, right? But now I know one of the D's. First of all, 5 kilometers is equal to, just going to do this off to the side here, is 5,000 meters, right? We also had to do that conversion so we could have them all the same unit. And if we took, and this is not a physics equation, what I'm doing right now. This is part of the sensing of the problem that you have to figure out. This makes sense. If I went constant for 4,902 meters, that means the little portion I sped up for would be the difference of that number and that number, right? That's the main part of this problem, realizing that. If you don't realize that, there's no way you could get it right. So we just take 5,000 and subtract off the 4902, and that would have to represent the D, which is in the accelerated motion column. Let's call it D2, because it's for part 2, right? Everybody with me? Any questions so far? Alright, now that I have that, I can solve for acceleration, right? So I find the correct kinematic equation. I know VI, T, and A need to find D. So, or in other words, the only one that doesn't have VF, which is equation number 2. Alright, so to finish this off, I'll just put an arrow down here. So it's D equals VIT plus 1/2 AT squared. And specifically, I'm using T for part 2 there and there, and this is going to be T for part 2. And I need to solve for A, so be careful with the algebra, right? So I should subtract this term over first. Let me go full screen on this. The VIT is going to have to subtract to this side, leaving me with 1/2 AT 2 squared over here. Then I'll do two things at once here. I'm going to multiply each side by 2, but be careful, I have a polynomial over here now, since I moved this. So I've got to put the 2 in parentheses. It needs to get multiplied by all of that. That's another mistake I see often on something like a rearrangement like this. Just putting the 2 there without parentheses. It's got to get multiplied through both sides completely, right? So that's got to go there, and then all that divided by the T2 squared, that's what's going to equal A. If we now carefully plug in other numbers, and don't make any calculator errors, we take D2, which was 98, minus the initial velocity, which was 4.3, times the 19.4, all divided by the same time squared, 19.4 squared. Keep remembering my suggestion, especially with big ugly fraction ones, I would figure this top out first, then divide by this. And if you do it right, you should get out 0.077 or 0.08 if you rounded it to 2 decimal places would be okay, meters per second squared. It's definitely the trickiest one, but as you can see, it really was kind of ripping like some of the straightforward problems backwards. We started with knowing the whole distance and having to break it apart, and everything fell into place. Any specific questions anywhere there? Yes? One thing I just want to point out, nobody brought this up today, but just from giving this problem a lot in the past. A common mistake on this problem is our students putting VF equals 0 here. But if you're thinking about the situation, that can't make sense. This is a race, right? Would you try to stop at the finish line of a race? No. So if you just try to pay more close attention to the scenario and what's going on. You would not stop right on the finish line. You try to go run it through it as fast as you can, right? So you cannot put VF equals 0. Nothing tells you to do that. You can't assume that unless it's telling you it would make sense to, and it does not. All right. If we're good with that one, questions on any of the other ones? Trish? The final answer to 36 is 34 meters. You want to see it? All right. I think this one's more like straightforward, like the example, but we'll get through it. An inline skater first accelerates from 0 to 5 meters per second in 4.5 seconds. So the very first part we're accelerating, right? And then continues at this speed we sped up to for another 4.5 seconds. So we end with constant velocity. Those two could always be in different orders. Don't assume one has to come before the other in these types of problems. Alright, so VI is 0, because it straight up tells me that, right? We go from 0 meters per second to a final velocity of 5 meters per second. And this part itself, I just want to be careful on this one. I think this happened in another one. We need to realize that the T over here is also 4.5, but not because this one is. It's just a coincidence that both parts are happening for 4.5. Does everybody understand that? This T and this T don't have to be the same number. And we got to be very careful with that because that's a common mistake sometimes. we're told we continue at this constant speed. So we sped up to this, and we're going to stay at it in the next part, right? There's my crossover piece of information. The v that stays steady over here is that. And yes, the t is 4.5, but that's just by circumstance here. It told us both of these were 4.5. It could have very well told us we stayed constant for 6 seconds, right? And that means that those two don't truly represent the same number because it just stays that way because we were told. Does that make sense? All right, so now that we get all this, we should be able to find, we'll call this D for part 1, D for part 2. We need to find the total distance during all this, find each of those and add them together, right? So I would use the only equation that doesn't have A in it, which is equation 4 for the accelerated motion part. So that would be, and it's already solved for D, so D1 will be equal to 1/2 VF plus VI times T. D5 plus 0. Half that times 4.5. Run those correctly, and we get about 11.25 for this part. Meters. All the units are good. No conversion necessary. D2, this is constant, so this is just using V equals D over T. Solve for D2, multiply the T over, plug in the numbers, 5 times 4.5. All the units are good here too. So D2 will be 22.5 meters. And we get about 30. What did I say the answer was? 34, yeah. So we get like 33.75, which in sig figs is around the 34. So D total, what they're asking, add those together, 33.75 meters. Make sense? Any questions? If you have, if something doesn't make sense, please ask, and I'll go back to whatever stuff does. You good? Questions on any of the other ones? Yes. 32, sure. We're coasting down a hill with an acceleration of 2 meters per second squared. When we get to the bottom, we're moving at 18. Then we stay steady at that 18 because it flattens off for another minute. So because it says we coast, we're going to have to assume we start from rest here, like you just went. You didn't like give yourself any pedaling or anything. So to begin with. So the accelerated motion part's the first thing. We're going to speed up as we go down that hill, right? So VI is 0. A is 2 meters per second squared. And that's good. We want to leave that positive. We're always assuming the way we're going is the positive direction. And if we're going to speed up down a hill, which we would, A would stay positive. We don't have to worry about throwing on a negative or anything like that. And at the bottom of it, we reach a speed. This will be our final velocity for this portion of 18 meters per second. Then that VF becomes the regular old V over here because we stay at that speed for a minute. I'm going to immediately convert that to 60 seconds. That's an A there, not a D. Okay, so same thing. We want the total distance, or how far total have you gone since you left the hilltop? I'd be finding each of those D's. So we'll call this one D1 and this one D2 and solve. So it looks like the only equation that doesn't have time in it is what we would need for the first part. So that would be VF squared equals VI squared plus 2AD. And VI 0, so I'm just going to get rid of that right away. If I solve this for D with that gone, we just divide by 2A each side. That would be VS squared over 2A. Pop in the numbers, and that's going to be 18 squared divided by 2 times 2 for the acceleration. Run those. 18 squared divided by 4. I get 81. I did that quick. Did anybody else get 81 there? Okay. I just want to make that a mistake. Alright, that's part of my answer. I got to go back over here. I'll just draw an arrow over here. This is just going to be v times t. This is the constant part, so that's going to be 18. I just noticed something dumb I did up there. That should be 18 meters per second right there. Got that. 18 meters per second times 60 seconds. For that part. And I get 1,080 meters. And then total those two up. What it's asking is going to equal, you're going to get somewhere like around 1,161 meters. Okay, does that make sense? Any other questions on that one or any other? The book answer was 1,160, but remember, when I read them out of the book, they're in sig-fig answers. So yours is probably sometimes going to be that, even if you didn't use them. But as long as you're close, you're fine. Not using sig-figs, it was one value off, right? It should still be very, very close. Even if you don't use sig-figs in most cases. All right, if we're good, you'll see two-part problems. Again, there's going to, once we finish free fall over the next day or two, you'll get, once we're at the full end of the chapter, we'll eventually get a mixed set of anything. Simple ones that were like on the last quiz, ones more like these, and ones that are considered free fall ones. You'll get a review set where they're all mixed up. So this won't be the last of these. There'll be a couple more in there. So on the full chapter test, there will definitely be at least one two-part problem. Alright, so I don't know how far we'll get into free fall. We probably won't get to the point where we're doing an example today, but that's okay. Going over questions is the more important thing today. There will be some notes I throw up here. But like always, it's up to you if you want to physically write them down. Because they're all going to be posted to the classroom anyway. For the next few minutes, just pay attention, basically. Okay? So, oh, Jake's dad stole my bowling ball and never gave it back, so I'm going to have to use a different one. Thanks a lot. I'm going to do something very simple up here. I'm going to see what conclusions some of you can make. Piece of paper, some kind of hard ball. It would be my bowling ball if Jake's dad didn't steal it. Did I mention that? Anyways, what's some conclusions or statements you could say on what you just saw happen? Both of those falling in front of you. Chris, tell me something. Okay, so the sum of what Chris just said, if you couldn't hear me, he said the paper fell not as fast because it's lighter than the heavier ball, basically. Right? Any other conclusions we could try to draw here? Good. Anything else? Alright, so let's go back and test some of these. Well, let's go to the first figure. Usually in most spheres, in most cases, the first answer to that, or the first conclusion you usually get, is somebody usually says that this fell faster because it's lighter. And this fell, or slower because it's lighter. This fell faster because it's heavier. So we got an issue here. Is this piece of paper the same weight as it was a moment ago? Yeah. Let me do the same thing again. Do lighter things fall at a different rate than heavier things? No. So now we can bring in, it seemed that way though, didn't it? So now we can bring in what we said over here, the fact that what got in the way a minute ago that didn't so much when I dropped it right there? Air resistance. All right, so if we could take all the air out of this room, we'd all be dead. But for a moment, if we were started dropping things, they would all fall at the same rate if you could get rid of air resistance. Because obviously we know what force makes things fall, and that's what? Gravity. And gravity could care less your size than your mass. It pulls everything the same rate. And some of us might already know that rate. We'll get to that in a second. But it doesn't discriminate. What makes it seem different is some things are more affected by air resistance than others, like that sheet of paper. Things that are pretty aerodynamic, a spherical shape is a pretty aerodynamic shape. Right? And if that spherical object is pretty dense, whatever that ball is made out of, similar to like what a bowling ball is made out of, that is stolen, I didn't have returned yet. Did I bring that up yet? It'll just kind of seem like the air is not even there bothering it. But we do have to be careful with air resistance, because some cases it might seem like it's not doing anything, especially on small drops. But we should all know just by life experience that air resistance builds up the faster and faster you go. So maybe something that we drop from like here to here doesn't have much effect on air resistance. Even this ball, which is a foam ball, from a small drop, especially like from there or even to the floor, air resistance pretty much is doing nothing to it. But if I drop this off like the top of this building, at some point it would change its motion because of the low mass of the object, even though it's pretty aerodynamic. Anyway, I'll get to more about air resistance in a second. The main thing is, if we get rid of the air, everything falls at the same rate. So I can't prove that to you with any objects right in front of you, but I can prove it to you. Obviously, crumpling up the paper is somewhat proof, but let's go somewhere where we can suck the air out of this thing. I'm a little disappointed. That's a new vacuum pump. I just got it last year and it still sucks. Now what's in here is a penny and a piece of paper. And when they fall with air, the piece of paper, just like the sheet of paper with that ball, lags behind. So that's not smoke, it's just condensation, by the way. I'm not burning anything. If I had a bigger tube, like we could put a cat in here. Probably be good enough. I'll put the seal off. Now that I put the air out, both fall at the same rate. Did everybody see from the back? Little by little air keeps back up. They both fall pretty much at the same time after a lot of air gets back in. If I really put in, it all back in, then there's a definite lag of a piece of paper because the air resistance stays way behind. So if you take air out of the equation, everything, it doesn't matter if it's a truck and a feather drop, both will hit the ground at the same time. The gravity pulls everything at the same rate. And does anybody have any idea what that number is, Carson? Yes, 9.8 meters per second squared. And we all know that meters per second squared, well, I hope we all know, is a unit for what? Acceleration. So we said earlier that obviously gravity is what does this, right? But we're still not at the point where we're worried about forces yet. We're worried about accelerations. That's what we've been studying the most, right? It is true that forces cause them, but our focus is still on accelerations, right? But the value, the magnitude of the acceleration, we call it the acceleration due to gravity, is 9.8 meters per second squared. And that means that as long as air is not in the way, if something falls every second, it speeds up by how much? 9.8 meters per second. That's what that means. Just like any acceleration. It's just a special one due to on Earth. Now different planets, moons, whatever, have different rates. That's not universal. That's for Earth. Okay? And we always say 9.8 is the value at or near the surface of the Earth. And it's truly actually an average value because the Earth isn't a perfect sphere, is it? Right? The force of gravity acts as if it originates from the center of the Earth's mass. We'll talk more about this later. But to understand it now, if it like originates from the center, the further you are away from the center, it will vary the amount of force. Because this is called what we say is a field force. And of course, you could be at sea level or you could be on the top of Mount Everest, right? So when we say an acceleration due to gravity on Earth is 9.8 meters per second squared, it's really truly an average of kind of like all altitudes, basically. But it doesn't vary much as long as your feet are literally on the ground or very close to it. I mean, it'll range, and it could go from a little bit under, like 9.7 something, to a little bit over, as long as you're at or near the surface. But once you start getting further and further away, like getting into the type of equations we got to do for orbits, which we'll do later in the year. Well, things that orbit out in space, right? They're not at or near the surface of the Earth anymore. It still feels a gravitational pull, but it would not be 9.8 meters per second squared anymore with acceleration. There'll be adjustable formulas later to getting that far away. But we typically, unless told otherwise, when we are in a situation with free fall, use 9.8 meters per second squared. And that's the magnitude. What would make sense for the direction to be? Since we're now doing problems on a vertical axis instead of all like this, right? It would probably make the most sense to make down to what direction? Negative. Alright, so for that reason, when we use G in the problems with free fall, it's going to be negative 9.8 meters per second squared. Later in the year, we might have equations where we just use its magnitude. That doesn't mean we're switching it and saying it's positive. We just might be using it in a scenario where we don't care about the direction. We just need the number, the value, the magnitude. But for now, it's always going to be negative 9.8. So how do we know something's in free fall if we're doing a problem? Well, there's basically 3 scenarios for free fall. And these are the notes I'm going to post. If you drop something, throw something up, or throw something down, that's all free fall. Now, when I throw something up, I'm not saying while it's in my hand once I release it. So while it's in my hand, it's not free fall, because the free in free fall means free of everything but the force of what? Gravity. Right? So when I throw something up like this, once I release it, it's in free fall. And of course, things that go up eventually do what? Come down, right? When I throw it downward, once it's out of my hand, now it's in free fall. Not when it's in my hand. And of course, just dropping it, letting it go, right? So any problems where it seems like any of those going on, that tells you it's a free fall problem. You're going to set it up as a free fall problem. We don't really need any new equations either. Because our kinematic equations, remember we always said, are good for uniform acceleration? Well, guess what? Freely falling under only the effects of gravity is a uniform acceleration. What does it stay uniform at the whole time? What number again for the 10th time? All right, negative 9.8 meters per second squared. So we could just use the same equations we already have, the 4 kinematic equations, and anywhere there's an A, we're going to plug in negative 9.8 if it's free fall. So most problems will not tell you negative 9.8 is a given. They'll just inform you in some way that one of these 3 things is happening, and you got to say, oh, this is free fall. I'm going to list my acceleration as negative 9.8. And actually, since it's such a special acceleration, it gets its own little symbol. Remember, this value is not the force of gravity. You're wrong if you say that. It's caused by the force. But because of its units, it's a what kind of value again? Acceleration. We refer to this number as the acceleration due to gravity, at or near the surface of the Earth. And we give it such a special number, such a super important number that now gets used all through mechanical physics. It'll pop up a lot. It's symbolized by little g. Don't use uppercase G because that's a whole other value back when we get into stuff with orbits. Lowercase little g represents that. So what we do with the kinematic equations, I didn't even rewrite them up here because you don't really have to. just, you got to know for any time you have a free fall situation, you apply them everywhere you see A, imagine a G there. Because it's a specific acceleration. We can just, no need to rewrite them all. You can if you really want, but they're all the same exact equations. Nothing else changes. But we got to make sure, though, that it is truly free fall. That means either air resistance is not present or negligible. What does negligible mean? Yeah. Right. Basically, just like with this ball especially. Do you think air resistance really has much of an effect on that ball? No. So if we're using things where air resistance, yeah, it's there, but it's basically making no difference. It's like it wasn't there, mainly because of the nature of the object. Good aerodynamics and pretty heavy. Both of those combined. Sometimes we call that surface area to mass ratio. It has a high enough one of those, even with air resistance, falls as if it was in free fall. But we got to be careful, because if we used any of these equations to figure out the rate of fall of a sheet of paper with air present, do you think they're going to be accurate? No. It's not free of significant things other than gravity. Air resistance, if it has a big effect on it, you can't use these. They won't be correct. Okay? What we can use, there is a way to study it. In this physics course, we don't cover it in an intro course. But it gets a little complicated when you start having fallings with air resistance, because a lot of different factors come in. I could drop, with air resistance, for something that really is affected by it, like a sheet of paper or feather or something like that. I could drop this thing 100 times in a row. Is it going to fall the same way every time? No. So it'd be kind of very difficult to say with air resistance. There are equations for it, but what's going to 100% happen? Usually there's a range that'll happen. And usually when scientists and engineers want to know something about the motion of things when there's significant resistance present, they test them in wind tunnels. You can get on those equations to test them experimentally to see what's happening the most consistently. So that piece of paper could fall many different ways, right? Or anything like testing aerodynamics of vehicles. You could perform all the equations you want, but sometimes the air conditions change, and could wind conditions, whatnot, and then you're really just in a range of what could happen. But if there's no air resistance, these are going to be 100% true, because gravity's pulling everything at 9.8. One little thing, this will help going into the problems tomorrow that we'll jump into. We're not going to quite have time today. But for the dropped condition, all right, remember, dropping is one of the three scenarios, right? This is something they won't tell you in a problem. You must assume if it says dropped. If a stationary object is dropped, you should assume that V initial is what? 0, because it's not moving initially, right? VI is 0. They won't tell you that. They won't tell you what G is, because you should identify, oh, this is a problem that's dropping. I know I'm going to use that as my acceleration, negative 9.8. If I drop that, I'm going to plug in 0 for VI. All right? Now, if we threw it up, it would have to tell you something about that. And direction, not that it didn't matter before, it becomes even more essential now. If I throw something up and they give you the D on the way up, you got to let it positive. But if I drop something, if I say I dropped something 2 meters, and it went that way, you better put a what on the 2? Negative. Because if you don't, the equation is going to think you dropped it and it went upward. Can that happen? No. So if you miss a negative in a situation like that, these equations map what really happens in the real world. And if it can't happen, you'll get a mathematical breakdown again. Like we saw with like negative times and stuff if we ever messed up stuff with accelerations on past problems, that'll happen here. So that's all the quick background to everything with free fall. We'll discuss more within problems. As soon as we get into here tomorrow, we'll do an example and then give you a problem set you could start on in class. No homework tonight, as long as you're caught up with everything.